Good afternoon, one and all. So today I am discussing about the fluid mechanics and hydraulic machinery gate class, and today my topic is turbines, hydraulic machines. So as we know, the turbine is a machine which is used to convert the hydraulic energy into mechanical energy, and from there the mechanical energy will convert the total energy into electrical energy. So today I am going to discuss the bits along with its explanation. So the first question is, hydraulic energy is converted into another form of the energy by hydraulic machines. What form of energy is that? So the answer is mechanical energy. Why? Because the hydraulic machines firstly convert the energy possessed by water into mechanical energy, and then it can be transformed into the electrical energy. So the next question, in hydraulic turbines, inlet energy is greater than the outlet energy. Is it true or false? Of course, it is true. The operating member which receives energy at the inlet should be more compared to the energy at the outlet. So definitely the inlet energy is greater than the outlet energy. Next one, which principle is used in hydraulic turbines? Newton's second law of motion is used for hydraulic turbines. So a hydraulic machine uses the principle of momentum. It states that a force is generated which is utilized in a turbine. Hence, the principle is used as Newton's second law of motion. The next question. The buckets and blades used in the turbines are used to alter the direction of the water. The buckets and the blades, whatever, in a Francis turbine or a Kaplan turbine or Prerana turbine, what are the type of turbine? In those turbines, the buckets and blades are used in the turbine just to alter the direction of the water. The turbines use blades and buckets to alter the direction of water, and it is used to change the momentum of motor. As momentum changes, force is produced to rotate the shaft to a hydraulic machine. Next one, so dash is the electric power obtained from the energy of the water. Hydroelectric power is the electric power obtained from the energy of water. The energy from the energy of water is also called hydropower. So hydroelectric power is the power obtained from the energy of the water. Next one, which energy generated in a turbine is used to run the electric power generator linked to the turbine shaft? So the answer is mechanical energy. The kinetic head and potential energies produced or converted to some useful mechanical energy. So this part of energy is available to the turbine shaft. Next one, hydraulic machines fall under the category of rotodynamic machinery. All the hydraulic machines are fall under the category of rotodynamic machinery. So the hydraulic machines uses the principle of rotation of the blades to alter the speed of water. Hence, these machines are fall under rotodynamic machinery. Next one, which kind of turbines changes the pressure of the water entered through it? The answer is reaction turbines. The reaction turbines which act on water will try to change the pressure of the water through its motion. Hence, these kind of turbines, the reaction turbines can changes the pressure of water entered throughout it. Next one, which type of turbine is used to change the velocity of the water through its flow? The answer is impulse turbine. In impulse turbines, potential energy is utilized to convert the kinetic energy, thereby changing the velocity of the water through its process. Next one, which type of turbine is a Francis turbine? Reaction turbine. Francis turbine is a type of reaction turbine as it changes the pressure of water through its process. Hence, it cannot be an impulse turbine. Then, next question, how many types of reaction turbines are there? Nearly 5 types of reaction turbines are there. They are namely as VLH turbine, Francis turbine, Kaplan turbine, Tyson turbine, Gorolov, Helical turbine. Next question. Maximum number of jets generally employed in an impulse turbine without jet interference can be 6 numbers. So equating equation of the initial jet velocity and energy of a turbine, we get the minimum number of jets to be 6. The overall efficiency of a reaction turbine is the ratio of actual work available at the turbine to the energy imparted to the wheel. So the overall efficiency of any turbine will be mechanical efficiency into hydraulic efficiency. In a reaction turbine, the draft tube is used to increase the head of water by an amount that is equal to the height of the runner outlet above the tail race. And because a draft tube influences performance of a turbine, it is located below the runner to declarate flow velocity. Next question. In reaction turbine, hydraulic efficiency is the ratio of work done on the wheel to energy that is supplied to the turbine. So we can say that in turbines, the overall efficiency is the product of hydraulic and mechanical efficiencies. Here the hydraulic efficiency is ratio of work done to the head of the water. Next question. Which kind of turbine is a Pelton turbine? It is a tangential flow turbine. Tangential turbine in one which water strikes runner in the direction of the tangent to the wheel of the turbine. So the Pelton turbine is called as the tangential flow turbine. In what, next question, in what type of turbine water enters in radial direction and leaves axial direction? So for mixed flow turbine. So only in a mixed flow turbine, the water enters in radial direction and leaves in axial direction. For a Francis turbine, the water enters in radial direction and also leaves in radial direction. And for a Kaplan turbine also, the water enters in axial direction and leaves in axial direction. But while coming to the mixed flow turbine, the water enters in radial direction and leaves in the axial direction. The next one, next question. How many types of turbines can you classify on the basis of direction of flow through the runner? So the answer is 4. So there are 4 types of turbines on the basis of direction of flow through the runner. That is, those turbines are tangential, radial, axial, and mixed flow turbines. Next one, in how many types can you classify the radial flow turbines? Nearly 2 types. So we can classify radial flow turbines into 2 types, namely inward radial flow turbine and outward radial flow turbine. Next one, into how many types can you classify the turbines on basis of head at inlet? So we can classify it as 3 types based on the head at inlet. Those are high head, low head, and medium head. Next one, among the following, which turbine requires more head? Obviously, Pelton turbine. So, except Pelton, remaining are reaction turbines and reaction turbines. In impulse turbine, pressure energy constant and only available energy is kinetic energy, and which is directly proportional to the head. So, for Pelton turbine, the required head is maximum. Next question. Head under which Kaplan turbine is operated as 10 to 70 meters. So Kaplan turbine is a reaction turbine and it operates at low head 10 to 70 meters and output power is 5 to 200 megawatts. Next one, head under which the Francis turbine is operated as 40 to 600 meters. So Francis turbine is also reaction turbine, but pressure energy is less when compared with the Kaplan turbine. Hence, head is in between 40 and 600 meters. Next one, the turbine is preferred for 0 to 25 meters head of water. So the type of turbine is Kaplan turbine. So Kaplan is a reaction turbine and its ranges of operation is between 10 to 70 meters, which has the output ranges between 5 to 200 megawatts. Next question, under what head is the Pelton turbine operated? Nearly 15 to 2000 meters. Pelton turbine is an impulse turbine. Only the available energy is a kinetic energy and which is proportional to the head. Hence, it requires high head. Theoretically, there is no limit to maximum value of the head for a turbine. Next question. So, which one is what is the difference between head race and tail race? So, it is known as gross head. So, gross head is the difference in elevation of water levels of fore, bay, and tail race. Next question. The head available at inlet of the turbine is net head. It is the net head is the head available, effective head used for production. And this is also called as the static gross head. Next question. Head loss due to friction is given by K into F into L into V square by D square. So where F is the friction coefficient, L is the length of penstock, D is the diameter of penstock, and K is constant and its value is 4. The constant determined from the given formula is 4. So that is 4 FLV square by 2 ZT. The difference between gross head and friction loss is known as net head. So the net head is the effective head used to calculate the power production, and it includes the elimination of the friction losses from the gross head. Next question. What is defined as the ratio between power delivered to runner and the power supplied at the inlet of the turbine? So the answer is hydraulic efficiency. Hydraulic efficiency is defined as the ratio between power given by water to runner of turbine and to the power supplied by water at the inlet of the turbine. Next one. Which among the following which is not an efficiency of the turbine? So the answer is electrical efficiency. Usually for a turbine we have only 3 types of turbines. That is mechanical efficiency, volumetric efficiency and hydraulic efficiency. So using mechanical efficiency and hydraulic efficiency we can calculate the overall efficiency, but we doesn't have electrical efficiency. Electrical efficiency is the ratio of work output and electrical power input to electrical machine. But turbine is a hydraulic machine which consists of only mechanical, volumetric and hydraulic efficiencies. Next question. The ratio of power at the shaft of turbine and power delivered by water to runner is known as mechanical efficiency. So due to mechanical losses, the power available at the shaft of turbine is less than the power delivered to the runner of the turbine. Hence, the ratio of power at shaft of turbine and power delivered by water to a runner is known as the mechanical efficiency. The product of mechanical efficiency and hydraulic efficiency is known as overall efficiency. Next one. Among the following, which turbine has highest efficiency? Obviously, the Kaplan turbine. Kaplan is the inward flow reaction turbine and is operated under head less than 60 meters. The vanes attached to hub are adjustable, and Kaplan is mainly operated in location where large quantity of water at low head is available. Next question. Which one is the ratio of volume of water actually striking the runner and volume of water supplied to the turbine? So the answer is volumetric efficiency. Volumetric efficiency is a ratio between volume of water actually striking the runner of turbine and volume of water supplied to the turbine. Next one. The expression for maximum hydraulic efficiency of Pelton turbine is given by 1 plus cos k by 2, where k is the outlet blade angle. So the hydraulic efficiency is defined as ratio between power given by water to runner of the turbine and to the power supplied by water at inlet of the turbine. Its maximum value is obtained by replacing u equals to v by 2. And it is 1 plus cos k by 2, where the k is the outlet blade angle. The next one is to obtain maximum hydraulic efficiency of Pelton turbine, blade velocity should be dash times the inlet velocity of the jet. The answer is half. Hydraulic efficiency is defined as ratio between power given by water to runner of the turbine and to the power supplied by water at inlet of the turbine. So this efficiency will be maximum when differentiating it with u, and it is obtained as u equals to v by 2. Next question. Among the following, which turbine has least efficiency? Pelton turbine. So Kaplan turbine has the maximum efficiency and Pelton turbine has the minimum efficiency. Why? Because the Pelton turbine is an impulse turbine where there is no theoretical limit for head due to high head. There is a loss due to the friction when water passing through the penstocks, hence its efficiency is less. Next question, the ratio of volume available at the shaft of turbine and power supplied at the inlet of the turbine is known as overall efficiency. So overall efficiency is defined as the ratio of power available at shaft of turbine to power supplied at inlet of the turbine. So, and which is also the product of mechanical and hydraulic efficiency. The next one, hydraulic coupling belongs to the category of energy transfer machines. So hydraulic coupling is a device used for transmitting the rotation between shaft by means of acceleration and deceleration of hydraulic fluid. Next question, the electric power which is obtained from hydraulic energy is hydroelectric power. And at present, which is the cheapest means of generating power? So the cheapest means of generating power is definitely hydroelectric power. The hydraulic energy is renewable source of energy in which potential energy of water is converted into mechanical energy, which is connected to the dynamo to generate electrical energy. Next question. Pipes of largest diameter which carry water from reservoir to the turbines is known as penstock. So penstocks are the channels which transport water from reservoir to turbines and which are usually made up of cast iron or concrete. Next one. Which one is an inward radial flow reaction turbine? So it is a Francis turbine. Of course, Kaplan and propeller are outward radial flow, axial flow reaction turbines, but Francis is outward radial flow reaction turbine. The important type of axial flow reaction turbines are propeller and Kaplan turbines. Axial flow turbine is a turbine in which the water flows axially outwards and the turbines fall into this category or propeller and Kaplan turbines. So which one is axial flow reaction turbines if vanes are fixed to hub of the turbine? So the answer is propeller turbine. If the vanes are fixed to the turbine, then it is propeller. If the vanes are not fixed, then it is Kaplan turbine. Next one, the Francis and Kaplan turbines are known as reaction turbines. Why? Because the pressure energy of water changes when it enters into the rotor. Next one, the specific speed of reaction turbine is in between 10 to 100 for reaction turbine. The specific turbines of reaction turbines such as Francis and Kaplan lie under the range of 10 to 100. Next question. The impulse turbine is generally fitted at above the tail race. The impulse turbine is fitted above the tail race because in impulse turbines, the pressure energy must convert into the kinetic energy for usage. Next question. The hydraulic turbines are classified based on energy available at inlet of the turbine, direction of the flow through the turbine, and head available at inlet of the turbine. Next question. Impulse turbine and reaction turbines are classified based on type of energy at inlet. So impulse turbine is the pressure energy firstly converts into the kinetic energy, but coming to the reaction turbine, which in which the pressure changes of water is present only when it passes through the rotor of the turbine. Next question, the tangential flow, axial flow, radial flow turbines are classified based on the direction of flow through the runner. High head, low head and medium head turbines are classified based on heads at inlet of the turbine. Next one, low specific speed, high specific speed and medium specific speed are classified based on specific speed of the turbine. So different specific speed of turbines are classified turbines based on their heads, namely Kaplan, Francis and Pelton. If energy available at inlet of the turbine is only kinetic energy, then it is classified based on type of the energy at inlet. If water flows in radial direction at inlet of the runner and leaves axially at outlet, then the turbine is named as mixed flow turbine. Next one, the Pelton turbine is operated under high head and low discharge. So based on the heads and discharges, the turbines are classified into Pelton, Francis and Kaplan. Pelton has high head and low discharge. Francis has medium head and medium discharge. Kaplan has low head and low discharge. Next question, Kaplan turbine is operated under low head and high discharge. The medium specific speed of the turbine implies Francis turbine. Francis turbine is a widely used turbine. It has the medium specific speed. High specific speed of a turbine implies Kaplan turbine. The velocity triangles are used to analyze flow of water, measure of the discharge, angle of deflection. So by using velocity triangles, we can determine discharge of the flow, angle of the deflection of the jet, and to measure relative velocity of jet with respect to speed of the wheel. Next one, in which of the following turbine inlet and outlet blade velocities of vanes are equal? So for Pelton well turbine, the inlet and outlet velocity triangles of the vanes are equal. So in Pelton turbine, each blade has the same angular velocity and same linear speed, unlike Francis and Kaplan turbines. Next one, the tangential velocity of blade of Pelton wheel is proportional to speed of the wheel. Usually, the velocity of blade is given by u equals to radius into angular velocity, from which the velocity is proportional to speed of the wheel. U is proportional to n and u equals to pi dn by 60. The next one, the value of coefficient of velocity is 0.98. The coefficient of velocity is defined as the ratio of actual velocity of jet at Vina contraction to the theoretical velocity. Its value is approximately 0.98. Next question. In which of the following turbine inlet whirl velocity and inlet jet velocity are equal in magnitude? So in Pelton well turbine. In Pelton turbine, the velocity of inlet is parallel to the splitter and is parallel to x-axis, which does not have flow velocity. Next one, in Pelton wheel, if outlet velocity angle of jet is acute angle, then outlet whirl velocity of the jet is x component of VR2 minus blade velocity. So why? Because by constructing velocity triangle, we came to know that whirl velocity of jet is equal in magnitude to that of x component of VR2 blade VR2, that is blade velocity. Next question. In Pelton wheel, if outlet velocity angle of jet is obtuse angle, then outlet whirl velocity is blade velocity in x component of VR2. So by constructing velocity triangle, we come to know that whirl velocity of jet is equal in magnitude to that of blade velocity in x component of VR2. Then the next one, in Pelton wheel, if outlet velocity angle of jet is right angled, then outlet whirl velocity is 0. So by constructing velocity triangle, we come to know that whirl velocity of jet is equal to 0, as x component of VR2 will be blade velocity. The next one, in Pelton wheel, the relative inlet velocity of jet with respect to velocity of vane is the difference between inlet jet velocity and blade velocity. So in Pelton turbine, inlet velocity of jet and the velocity of vanes are in same direction and different magnitude, hence the relative velocity is found by calculating its difference. Then the next question, in Pelton wheel, if angle of deflection is not mentioned, then we have to assume the value as 165 degrees. So it is the standard value for deflection of the jet, which is found by performing several experimental operations. Next question, the work done per unit weight of water jet striking runner blades of the Pelton turbine is given by the expression VW1 plus VW2 into U by G. So generally the work done is force times the velocity, and expression for it is PQ into VW1 plus VW2 by into U by G, and work done per unit weight gives VW1 plus VW2 into U by G. The next question, in Pelton turbine, The energy available at inlet of the runner, that is at outlet of the nozzle, is known as runner power. In Pelton turbine, the energy available at inlet of the runner, that is at outlet of the nozzle, is known as the runner power. The energy available in penstock is water energy. Next question. In Pelton turbines, the expression for power delivered at inlet to runner is given by W, that is rho into G into VW1 plus VW2 into U by G into, or rho G into VW1 minus VW2 by into U by G. Simply it is plus or minus 2. Generally, the work done is 4 times the velocity and the expression from it is PQ. In Pelton turbine, the runner power is more when compared with power available at the exit of the nozzle. But if it is a false sentence. The runner power is less when compared with the power available at exit of the nozzle and due to frictional losses. Next problem. Kinetic energy of a jet at inlet of the turbine is given as 0.5 into rho A V1 into V1 into V1. So here rho is the density of the liquid, A is the area of the jet, and V1 is the inlet jet velocity. So the expression for kinetic energy is produced of half minute mass and square of velocity. The mass can be written as density time volume. Next one, the force exerted by a jet of water in the direction of jet on a stationary curved plate Fx is given as rho A V into 1 plus cos k. So we can write it as rho A V square into 1 plus cos k. So generally the force is rate per change uniform. Change of the momentum. In curved blade of the angle, k changes of momentum will be rho A V into 1 plus cos k. Next one, the force exerted by a jet of water in the direction of the jet on moving curved plate is rho A V into V minus V into 1 plus k. So generally the force is a rate of change of momentum. In curved blade angles, k changes of momentum will be rho A V into V minus U into 1 plus k. Here the relative velocity is considered then absolute velocity. Next question. Calculate work done by jet per second on the runner where discharge is 0.7 cubic meter per second. Inlet and outlet where velocities be 23.77 and 2.94. So as we know the expression for work done per second as rho G into VW1 plus VW2 into U by G. On substituting the above given values, we get the solution as 187 kilowatts. Next question. The power supplied at inlet of the turbine in SI units is known as water power. So the power supplied at inlet of the turbine in SI units is known as water energy, which contain both kinetic energy and pressure energy. Next one, the expression for water power in Pelton wheel is given as rho Z QH in kilowatts. So expression for water power of Pelton turbine is a potential energy of water which is converted into kinetic energy. So it can be written as rho Z QH in kilowatts. Next one, the hydraulic efficiency of Pelton turbine will be maximum when blade velocity is V by 2, that is U equals to V by 2. The expression of water in Pelton wheel turbine is given as rho Z QH into KW. The hydraulic efficiency of Pelton turbine will be maximum when blade velocity is equal to V by 2 only. Next one, in Pelton turbine, which which is defined as the ratio between power delivered to the runner and power supplied at inlet of the turbine, that is hydraulic efficiency. The maximum efficiency of Pelton turbine is given as 50%. So we know that the efficiency will be maximum when blade velocity is equal to half of the jet velocity, that is U equal to B by 2. Next one, in Pelton turbine, the product of mechanical efficiency and hydraulic efficiency is known as overall efficiency only. Next one, among the following, which turbine has the least efficiency? Pelton turbine. So in Pelton, which is the ratio of volume of water actually striking the runner and volume of water supplied to turbine, overall efficiency. So next one, in the expression for overall efficiency of turbine, which is rho by K into G into Q into H, where K is known as density of the liquid. So the overall efficiency is defined as the ratio of power available at shaft of the turbine to power supplied at inlet of the turbine, which is also the product of mechanical and hydraulic efficiency. So its expression is given by P by Kg rho into K into G into Q into H, where K is the density of the liquid. Next one, in Pelton turbine, hydraulic efficiency is the product of mechanical efficiency and overall efficiency. No, it's false. The next one, the expression for hydraulic efficiency is given by 2 into V1 minus U into 1 plus cos K into U by V1 into V1. So, where V1 is inlet of the jet velocity, U is the blade velocity, and K is outlet blade angle. So we can say that the hydraulic efficiency is the ratio of power delivered to the runner to power supplied at inlet of the turbine. Turbine, upon substituting the mathematical terms, we get the expression as follows. Next one, in Pelton turbine, the inlet velocity of jet is 85.83 meters per second. The inlet and outlet whirl velocities be 85.83 and 0.143. And blade velocity is 38.62. Then its hydraulic efficiency will be. So substituting the above given values expression for hydraulic efficiency is given as 2 into VW1 plus VW2 into U by V1 into V1. So then we get, by substituting all the values, we get 90.14%. Next problem, the design of Pelton wheel means the following data is to be determined. So the data is width of the bucket, depth of the bucket, and number of the buckets. All are required for design of Pelton wheel. Next one, the width of the buckets of Pelton wheel is 5 times the diameter of the jet. Next one, the depth of buckets of Pelton wheel is 1.2 times the diameter of the jet. The next one, the ratio of pitch diameter of Pelton wheel to diameter of the jet is known as jet ratio. So the ratio of pitch diameter of Pelton wheel to the diameter of jet is known as the jet ratio. Next one, find the diameter of the jet D if the jet ratio M and the diameter of the jet D small d are given as 10 and 125 mm. So expression for jet ratio M equals to capital D by small d. So we have the value for small d and M. So substituting those values in the formula, then we get capital D equal to 1.25 meters. Next one, the number of buckets of Pelton wheel is 25 and the diameter of runner is 1.5 meters. Then calculate the diameter of the jet is 85 mm. So the expression for measuring number of buckets is 15 plus diameter of runner by 2 times the diameter of the jet, that is capital D by 2 into small d. 15 plus capital D by 2 into small d. So substituting all the values capital D and small d, then we get the value as 85 mm. The next one, excuse me. In most of cases, the value of jet ratio is 12. So jet ratio is 12 because in most of Pelton turbines, the diameter of runner is 12 times the diameter of the jet. Next one, the number of buckets on the runner of the Pelton wheel is given by the expression. If D is the diameter of the runner and small d is the diameter of the jet, then expression will be 15 plus capital D by 2 into small d. Next one, which is obtained by dividing the total rate of flow through the turbine by rate of flow through the single jet, that is number of jets. The total discharge is sum of individual discharges. Hence, by dividing total rate of flow through the turbine by rate of flow through the single jet, we can get the number of jets, that is capital Q by small q. And the next one, if the diameter of the jet is 85 mm and the diameter of runner is 1.5 meters, then calculate the width of the buckets as 425 mm. So the formula will be multiplying with all these things. So the expression for measuring the width of bucket is 5 times the diameter of the jet, that is 5 into 85, that is 425 mm. Next problem. If diameter of jet is 85 mm and diameter of runner is 1.5 meter, then the depth of the buckets is given as 102 mm. So the expression for measuring depth of the bucket is 1.2 times the diameter of the jet. So we have the diameter of the jet 85 mm and we have the equation 1.2 times the diameter of the jet. So substituting all this, we can get the value as 102 mm. Next question. If diameter of the jet is 85 mm and diameter of the runner is 1.5 meter, then calculate number of buckets on Pelton wheel approximately. So the expression for measuring number of buckets is 15 plus capital D by 2 into small d. So substituting the capital D value and small d value, that is 1.5 and 85, then we can get the value as 25. Next question. The ratio of diameter of jet to diameter of the runner is 1:6. So to obtain Pelton wheel of higher efficiency, diameter of runner is 5 times the diameter of the jet by considering several experimental observations. Next one, what is the water flow direction in the runner in a Francis turbine? So the water flow direction is radial and then axial. Next one, in the velocity diagrams for Francis turbine, which of the following velocity direction is along the blade curvature? So the answer is VR1. VR1 is the relative velocity of the water flows as seen from the table, from the blades. Thus, the relative velocity is along the direction of the curvature of the blade. Next one, in the figure shown below, which of the following angles replace the question mark? So we have the question mark at this place, and at this place the term is guide vane angle at inlet. So the here we have all R as 1. So it is at inlet values, and at this portion we have the guide vane angle at inlet. Next one, in the figure shown below, which of the following type of runners has the blade curvature as shown in the above figure? The arrow denotes the direction of the blade motion. So the answer is slow runner. So the explanation is, fast runners have forward curved blades, where slow runners have backward curved blades. The blades shown in the figure are backward curved blades of a runner, which are used for slow runners. Next problem. Next one. Which of the following efficiencies for Francis turbine is described as the ratio between the power produced by runner to power supplied by the water at inlet? So the answer is hydraulic efficiency. Next one, which of the following efficiencies for Francis turbine is described as the ratio between total quantity of water over runner blades to total quantity of water supplied to turbine? So the answer is volumetric efficiency. The definition of volumetric efficiency is, Francis turbine states that it is the ratio between the total volume of water flowing over the runner blades to the volume of the water entering into the turbine. Next question. Which of the following efficiencies for Francis turbine is defined as the ratio between power available at shaft to power produced by the runner? So the answer is mechanical efficiency. Next one. Which of the following efficiencies for Francis turbine is defined as the ratio between power available at shaft to power supplied by water at inlet? So the answer is overall efficiency. And next question. The whirl velocity at inlet of Francis turbine is given by 20 meters per second. The blade velocity is given as 35 meters per second. What is the hydraulic efficiency for a head of 100 meters? So the answer is 70%. The explanation is the hydraulic efficiency of a Francis turbine is given by eta H equals to VW1 into U1 by GH. So substituting the values of given parameters in the equation, we can get the efficiency as 70%. So another one, same question. The desired hydraulic efficiency of a turbine is 80% at a whirl velocity of 20 meters per second and a head of 100 meters. What should be the blade velocity of the turbine at inlet in meters per second? So for that one, again we are going to use the same formula for hydraulic efficiency, eta H equals to VW1 into U1 by GH. So substituting all this, we can get the blade velocity at the inlet as 40 meters per second. Next problem. The input water power of the Francis turbine is 1.25 times the runner power. What would be the hydraulic efficiency of the turbine in percentage? So we can say that the definition of hydraulic efficiency in a Francis turbine states that it is the ratio between the runner power to the shaft power. If input power is 1.25 times the runner power, then the runner power is 1 by 1.25 is equals to 0.8 times the water power. Hence, the hydraulic efficiency is 80%. Next problem. The volume flow rate into a Francis turbine is Q meter cube per second and 0.25 Q meter cube per second. The volume of water do not flow over the runner blades. What is the mechanical energy and mechanical efficiency of the turbine in percentage? So the answer is given as mechanical efficiency cannot be found out from the given formula. Next one. The volumetric efficiency of a Francis turbine is given to be 90%. If the volume flow rate through the turbine is 25 meter cube per second, then what is the rate of flow of water over the runner blades in meter cube per second? So for this one, the definition of volumetric efficiency in a Francis turbine states that it is the ratio between total volume of water flowing over the runner blades to the volume of water entering the turbine. Hence, Q is 25 meter cube per second. The volume of water over runner blades is 0.9 into 25. So the answer is 22.5 meter cube per second. Next question. The volumetric efficiency of a given turbine is 80%. If volume flow rate of water is given to be 30 meter cube per second, find the volume of water not flowing over the runner blades per second. So the volume of water flowing over runner blades is 0.8 into 30 efficiency into the discharge. So then we get 24 meter cube per second. The volume of water not flowing over the runner blades would be 30 minus 24, that is 6 meter cube per second. The next problem. The power available at the shaft of a turbine, shaft of a Francis turbine is 1 megawatts. The volume flow rate of water in 25 meter cube per second, which whirl velocity at inlet is 10 meters per second and blade velocity is 5 meters per second. Find the mechanical efficiency. So to calculate the mechanical efficiency, the formula is eta M equals to shaft power by rho Q into VW1 into U1. So substituting the given values into the question, into this equation, then we get the mechanical efficiency as 80%. Next problem. The whirl velocity at inlet is 15 meters per second and blade velocity is 10 meters per second. The volume flow rate of water in 20 meter cube per second. Find the power output available at the shaft if the mechanical efficiency is 95% in megawatts. So mechanical efficiency is given as eta m equals to shaft power by rho q into Vw1 into u1. So substituting the given values in this equation, then we get the shaft power as 2.85 megawatts. Next problem, the power output of the shaft is 5 megawatts. The volume flow rate of water in 10 meter cube per second at an available head of 60 meters. Then find the overall efficiency of the turbine in the percentage. Here, acceleration due to gravity G is taken as 10 meter per second square. So, the formula for overall efficiency is shaft power by rho G QH. So, substituting all the values in this equation, we get the overall efficiency as 83.33%. Next one, the volume flow rate of water in a 10 meter cube per second at an available head of 60 meters. That is, find the shaft power in megawatts if the overall efficiency of the turbine is 90%. So the overall efficiency of turbine is Francis turbine is given by eta O equals to shaft power by rho G QH. So substituting all the values we get 5.4 megawatts. The next problem, the hydraulic efficiency of a Francis turbine is 90%. Mechanical efficiency is 95%. Volumetric efficiency is 100%. Then find the overall efficiency. So we know that overall efficiency is the product of hydraulic efficiency, mechanical efficiency and volumetric efficiency. So multiplying all the efficiencies, then we get the overall efficiency as 85.5%. In a Kaplan turbine, what is the direction of water flow? So the answer is axial and then axial again. For which of the following values of available heads may Kaplan turbine be used? Usually 50 meters. Why? Because the Kaplan turbine is a low head turbine. The low head turbines are ranges from 0 to 60 meters. In this type of low head turbine, the guide vanes are fixed to the hub of the turbine and are not adjustable. What is this type of turbine called? So it is called as the Francis turbine. In a Kaplan turbine, the guide vanes are adjustable and not fixed to the hub of the turbine. Francis and Pelton turbines are not low head turbines. So it is a low head turbine, hence it is a Kaplan turbine, not the Francis turbine. And the next problem, the velocity of the flow through the Kaplan turbine is 25 meters per second. The available head of the turbine is 60 meters. Find the flow ratio of the turbine. So to calculate the flow ratio, the formula is Vf1 by square root of 2gh. So substituting Vf1 value, g value and h value, we get the flow ratio psi as 0.72 b. And the next problem, for the figure given below, find the missing terms in the order of 1, 2, 3 and 4. So from the inlet velocity triangle, we can write as Vw1 is along the direction of u. Hence, 1 is replaced by Vw1. The angle between V1 and u is alpha 1. Hence, alpha 1 is replaces 2. Then 4 will then be replaced by VR1 and 3 will be replaced by beta 1. Since beta 1 is the angle between VR1 and U1. So the answer is VW1, alpha 1, beta 1 and VR1. And the next one, draft tube is also called as the straight divergent tube. So draft tube is one of the most commonly used in the Kaplan turbine. It works as an outlet at the Kaplan turbine. And draft tube is also called straight divergent tube. Next problem, what is the maximum value of efficiency in a draft tube? So the maximum efficiency is 90%. It cannot exceed more than 90% because of the head loss due to flow of the liquid. Next one, the efficiency of a draft tube is directly proportional to its velocity. So efficiency of the draft tube gives difference of the kinetic energy between the inlet and outlet tube losses. Hence it is directly proportional to its velocity. Next one, the specific speeds are used in pumps to determine suction specific speed. Next one, low specific speed in hydraulic head is developed due to centrifugal force. The next question, the specific speed is the speed of the turbine which is similar to its aspect ratio. Why? Because the specific speed is the speed of the turbine which is similar to aspect ratio. The specific speed is denoted by NS and it is used to characterize speeds in turbo machinery. Some of the main examples of a turbo machinery are turbines. The specific speed plays an important role in the turbine. Next question. Specific speed develops a unit power under a unit head. The specific speed of Pelton wheel with a single jet is ranges from 8.5 to 30. The specific speed of a Pelton wheel with multiple jets is ranges from 30 to 51. The specific speed of a Francis turbine is ranges from 51 to 225. The specific speed of a Kaplan turbine is ranges from 355 to 860. Which among the following is not a unit quantity of the turbine? So the answer is unit temperature. Unit discharge is unit speed and unit power are the three basic functions of the turbine. It plays an important role in determining specific speeds and to increase the overall output efficiency of the turbine. Next one, unit speed is the speed of the turbine operating under 1 meter head. So by keeping the head as 1 meter, the unit speed can be calculated. Unit speed of a single jet in a turbine is 800 meters per second. So unit speed of a single jet in a turbine is around 800 meters per second. The most commonly used symbol of unit speed is N suffix U. And unit speed is the speed of the turbine operating under 1 meter head. Thus the option is C, 500 meters. Answer is D, that is 800 meters per second. The unit speed is the speed of the turbine operating under 1 meter heat. Okay. So the unit discharge is the discharge through the turbine when the head of the turbine is unity. So unit discharge is the discharge when the head of the turbine is unity. Next question. The constant head curves are also called as main characteristic curves. The constant head curves are also called as the main characteristic curves. It helps in determining the overall efficiency of the turbine by drawing the curves with a different set of parameters that play a major role in determining the performance of the turbine. Next question. All the characteristic curves are drawn with respect to unit speed. All the characteristic curves that specify the different parameters in a turbine are drawn with respect to its unit speed. Unit discharge, unit power and overall efficiency versus the unit speed is drawn. Next question. Constant efficiency curves are plotted using constant speed and constant head curves. So constant efficiency curves are plotted using both constant speed and constant head. The constant efficiency curves are also called as the Michel curves. It helps in determining the overall efficiency of the turbine by drawing the curves with a different set of parameters that play a major role in determining the performance of the turbine. Up to that, we have completed the turbines. In the next class, we will discuss the remaining. Okay, thank you everyone. In the next class. ఇలా దానికోసం లాస్ట్ షోకి వెళ్ళారండి రికార్డ్ అయిందా